All right, welcome
Hi.
to today's meeting. It's a great pleasure to have Art Louis today. Art did his undergrad degree in theoretical physics at the University of Utrecht before he went on to get his PhD in theoretical physics with Neil Ashcroft from Cornell University. After that, he was a postdoc and a Royal Society University Research Fellow in theoretical chemistry at Cambridge University before he came to Oxford, where he now is a professor in theoretical physics. Today, he will talk about why do neural networks generalize in the overparameterized regime, and we're looking forward to his talk. Thank you very much, Art.
Thank you very much, Fabian, for this talk. Let me just make sure that for some reason, as you spoke, my Zoom disappeared. Okay. Can you see my cursor moving on this? I think that's the Zoom. Good.
Yes.
So,
but you're not in full screen.
Okay, thank you. That was probably what's it. Super. All right. So I'm very grateful to Fabian and to the other organizers for inviting me. It's a great privilege and honor to speak to you. It's very exciting times for physics and machine learning for a number of different reasons. I think partially because machine learning is going through enormous and very exciting developments, and partially because these are trying to be applied to physics. But what I'm going to be talking about more is using really a kind of physics-inspired intuition to understand some basic properties of machine learning. And I'll be speaking mainly as a physicist, so some apologies to the mathematicians and hardcore machine learning people. I will be stepping over various subtleties with big fat boots. And while I'm speaking, my very brilliant DPhil student, Guillermo Valle-Perez, will answer in the chat while we're going, just because I find it hard to talk and chat at the same time. So the question is really, why do deep neural networks generalize in the overparameterized regime? Roughly speaking, why do they work so well when there are many more parameters than there are data points? And physicists are taught from a very young age that this would be a bad thing to do. So never use more parameters than data points, and actually try to use as few parameters as possible. And so when I first saw this, I got quite interested in this question. It seemed odd. And so what I'm speaking about today are my kind of playing around in this area, aided by a series of very brilliant students. All right. So just as a summary for the physicists, what is learning about? Here's a beautiful quote by Alan Turing, where he said, instead of trying to produce a program to stimulate the adult mind, why not rather try to produce one which stimulates the child's? If this were then subjected to an appropriate course of education, one would obtain the full adult brain. That might be a bit ambitious, but it's a helpful way of thinking about it. So you can divide your problem into two parts, the child program and the education process. So the education process I'm going to mention, mainly described today, is called supervised learning, where I give something a bunch of data and ask some kind of program to learn from that data and then make predictions. And here's an example of the kind of problem that we might want to be able to learn if we're doing machine learning. So, and this will get me to a little sub-theme, which I'll explore first before getting into the actual problem at hand. So let's say that you're a doctor and you have a little decision table for COVID-19 patients, and you ask yourself, should you send this person to the hospital? Well, somebody comes to you, they've got a fever. 1 will mean yes, 0 will mean no. So fever, yes. Cough, yes. Loss of sense of smell, yes. Body ache, yes. Recently traveled to a hot spot, yes. Over 50, yes. Heart problem, obese, diabetes. It's bad, but we send you to the hospital right away. And you can think of other combinations, so everything the same, except perhaps you're younger, in which case I'll still send you to the hospital if you're obese and have diabetes. But if you're younger than 50, but are otherwise healthy, I'll just say to you, sorry, mate, hospital's full, go sick it out at home. And you can think of more and more combinations of this type. Perhaps you have some of the symptoms, but not other ones. Perhaps you have some of the risk factors, but not other ones, etc. And so what a machine learning algorithm might want to do is to take some examples of doctors making these kinds of decisions, and then hopefully being able to learn the rest of the function without having to see all possibilities. And you can think of many of the examples of things that we try to learn have this type of structure to them. So this is a kind of Boolean choices, and there's a Boolean function. And blue here on the left is the Boolean function that tells me for each set of answers to my 9 questions whether I give a true or a false. Now here's something that, which is what initially got me interested in this problem, is not so much learning itself, but the question of hyper-astronomical numbers. So if I have n questions, there are 2 to the n possible answers. It could be 1 or 0. How many Boolean functions are there? Well, for each answer, of which there are 2 to the n, there are 2 possible functions. A function could say 1 or 0. So there are actually 2 to the n possible Boolean functions. So even for these 9 questions that I've given you, of which there are 512 possible answers that a patient can give, there are 2 to the 512, or about 1 times 10 to the 154 different possible functions. Now there are, we think roughly 10 to the 86 elementary particles in the observable universe. So I like to call this a hyper-astronomical number. It's quickly is something which is larger than, say, the number of atoms in the universe or the size of the universe. And what you'll see in these kinds of combinatorial problems is that the combinatorial explosion of possibilities very rapidly becomes hyper-astronomical. And interestingly, in the famous Lighthill report in the 1970s that effectively closed down artificial intelligence research in the UK for quite a while, this kind of argument saying the number of possibilities grows exponentially, hyper-astronomically, we'll never be able to learn all of this or figure it all out, so artificial intelligence won't work, was one of the arguments. And I'm bringing this up because as physicists, you shouldn't be surprised that these numbers grow very quickly. And computer scientists are taught this from an even younger age. We're used to this exponential growth is very fast, but I was still surprised by the actual number of functions you get even for such a simple question. And this is going to become important in a minute. All right, so this is a simple example of a kind of a Boolean truth table. But what are some other examples from history of people doing this kind of exponential counting? Well, it turns out that taking powers of 2 was something that was done throughout history, particularly as a kind of recreational mathematics. So here is the oldest example I could find, which is from an old Babylonian tablet from Mari, just on the border with Syria and Iraq, where a scribe put on the back of this clay tablet that he had a barleycorn on the first day, then 2 on the second, 2, then 4, then 8, all the way to 30. And then he counted the total number of barleycorns of that day, which comes to about 47 tons of barley. And that number 30, doubling questions number 30 are very common throughout this area, particularly along the Silk Route. And you find another example of this kind of doubling, which is also very famous, from numbers like 64, which is another popular number to use. And that comes from, for example, chess. So here's a very famous story of the invention of chess in Shamana, the Book of Kings, by Ferdowsi, the great Persian poet. And a bit later, the barleycorn and chessboard story was recounted by another great polymath, I can never pronounce his name right, Kali Khan, who tells a story of the king being so enthralled by this new game of chess that he offers the inventor the option to have 1 barleycorn have basically any present, any gift he wants. The inventor says, I'd like to have 1 barleycorn on the first, 2 on the second, etc. You can do the math. It turns out there are 18 quintillion barleycorns, which is roughly 1,000 times the world's current annual wheat production. So what this tells us is that if we just do kind of blind counting, that the number of possibilities grows hyper-astronomically large very quickly. And you may wonder, why am I telling you this? Well, there's actually a system that we're all very used to where this happens all the time. That is life. So if you look at the basic building blocks of life, so take, for example, proteins. So proteins are made of an alphabet of 20 different letters, amino acids. So if I have a protein of length L, I can make 20 to the power L different sequences. And then you can ask yourself, well, how much would it weigh if I made every possible sequence of a given length? If I take every length 37, it would weigh more than the Earth. If I made it length 58, it would weigh more than the observable universe, which is anything above 58 becomes essentially hyper-astronomical. Now, if you're not a biologist, you may wonder, well, is this big or small, 58? it's actually extremely small. The mean length of proteins in your body is 476. And if I made every possible protein of length 476, it'd be 10 to the 500 times the mass of the observable universe, which is extremely large and unimaginably large number. And so you can do the same for RNA, which is another really important biomolecule that we're partially made of. And a certain fraction of RNAs are functional, so they do things like catalysis or structure, and they have 4 letters, but the same thing happens. By the time you get to length 126, every RNA of length 126 may more than the observable universe. And every length 55 RNA, which is what I'll just show you in a minute, if I made every single strand, this is extremely small RNA actually, it weighed 10 to the 10 kilos. Now, why is that interesting? It's interesting because there are good evidence that we keep finding certain structures in these molecules again and again. So what these molecules typically do, they're a linear sequence of different letters, and they fold into a 3-dimensional structure that's pretty well repeatable. So you can fold them and unfold them, and they will, in the right conditions, fold to exactly the same shape. And their behavior is very much dependent on their shape. There's a very beautiful experiment by Jack Szostak and the collaborators where they did in vitro evolution experiments. So they took little strands of RNA of length, say, on the order of 55, which are initially just random, and then they select on ones that have some desired activity. So in this case, the desired activity was self-cleaving enzymatic activity and enzyme behavior. So it's something that cuts itself. And they selected on this and repeated it. And if you keep doing this, eventually your solution gets enriched with the right kind of molecule. It's a kind of in vitro evolution system with a cost function that pushes you towards a certain type of function, a structure. Now, what was fascinating in this paper is that every time they did this, they always found this particular 3D structure, which is called the hammerhead ribozyme. And I was completely flabbergasted by the experiment because there are 10 to the 10 kilos of stuff you could make of length 55, and yet they found the same thing again and again using only about a 100th of a gram of material. So they've only searched about 1 in 10 to the 15th of the space, and they find the same thing again and again. So even though the number of sequences is hyper-astronomically large, there's something about the system which is allowing it to find the same thing again and again and again. And that's surprising, to say the least. Now, the nice thing about RNA is that people have worked out some nice ways of calculating how these things fold. Calculating the full 3-dimensional fold is still very hard, but you can do what's called a 2-dimensional fold or a secondary structure, which is really just saying which molecule binds to which molecule in this particular sequence. So these letters are the 4-letter alphabet, and there's little rules, basically some thermodynamic binding rules. You calculate a partition function, and you look for the lowest free energy, and that will give you the lowest free energy structure of this system. And there are rapid ways of calculating this. So if I give you the sequence, I can find in a very short amount of time what the structure is that minimizes the free energy of this sequence. And so then you can ask a question, which is, if I pick sequences at random, as Szostak and his collaborators did, do I find this structure very easily? Now, naively, you would say, well, no, because there's enormous number of these sequences. Why would you find the same structure more than once? But one thing we know about these systems is that there's a redundancy. So many sequences can map to the same structure. You can flip a few of these things, you'll get the same ground state structure. And here's an example of a simpler system. So here's a length 15 RNA, where it starts here, G, C, G, G, A. So G is bound to the C. I count this from one corner. 1, 2, 3, 4 are bound to these. These ones are not bound, and this one is not bound as well. I can abstract that out to this simple dot bracket notation. So bracket means I'm bonded, bracket, 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 bracket. The first 4, dot, 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 dot. The next 4, and then close bracket, right? Close bracket, and I can see who binds to whom, and the 3 dots on the left. So I can ask a question like, if I fold all sequences of this length 15, what would be the distribution of structures that I get? And what we found is if you folded all length 4 structures as 4 to the 15 to the 30, so that's a billion. There's only 431 shapes that they map to. But there's something else very striking, which is that some structures, like this one right here, have about 12 million going to it, whereas this one only has 2 sequences for which it is the ground state. So I'll count what people in this field call this number is the neutral set size. It's the set of all sequences that map to it, but you can think of it as a kind of entropy as well, or log of that would be the entropy. And so here I've got the log of the neutral set size, like the entropy, sequence entropy, and here I've ranked these structures from the most likely to the least likely. And I see that these drop by many orders of magnitude, and in fact, the first 26 of these take up 50% of the space. And you'll see in a minute why this might be interesting for learning, but this is quite striking, and we were very surprised by this and trying to understand why this was. And it turned out that almost every other map from sequences to some biological function that we could calculate showed this extremely strong bias with a small number of possible outputs taking a dominant number of input sequences. For RNA, in fact, we did this for the length 55 RNA, which is the one that Schultz-Stacken experiments did. Here's the neutral set size, here's the log of the rank. And what you see is that this thing is highly biased. There's a small subset of structures with very large number of sequences mapping to them, and many with fewer. And what's interesting is 2 things. First of all, this hammerhead ribozyme, which is what we found in the experiment and is in fact found in all the major classes of life, so it's evolved independently many times, is one of these structures that has an enormous number of sequences mapping to it. And here in green, I show you 504 sequences from an RNA database. These are what's called functional RNAs, or RNAs which are not slave to DNA like messenger RNAs, but they're doing something in the cell, like catalysis or like structure. And the ones that are found in nature are overwhelmingly these ones that are easy to find, with many sequences mapping to them. And so, in fact, what's even more surprising, but that's for a different time, is that the distribution of them, so the frequency with which you find them in nature, is predicted by simply randomly sampling the sequences and seeing how often something appears. In other words, although the evolutionary process is not working that way, it's going, in principle, along some kind of fitness gradient to maximum fitness. On average, when you look at what kind of function is found, the randomly sampling the sequences is a good prediction for what you find in nature. And so we spent quite a bit of time working out why the dynamics have this kind of output. And to first order, just because these systems are hugely biased. And so when you're an evolutionary run, you're only going to see a small subset of the possibilities, and those are the ones that are going to be found in nature. So the first part of the story is that for these kinds of evolutionary systems, we see an extremely strong bias, and it seems to be very common. And so we start asking ourselves, why do you have this bias? Why in this system is there this very strong preference for a very small subset of all the things that are possible? So in this case, the hybrid ribozyme, there are about, we think, 10 to 13 possible structures that this length RNA could have. It's very possible that in that space, there are extremely good other catalysts, but we don't know because their space is too big to search. And so it looks like what nature does is it finds things that are good enough, and those are things that it finds quickly, and that's basically where it stays. So why this strong bias? I sent the students to start looking for sources of bias, and actually what we decided to think about is a kind of very vague intuition, which I want to explain to you now. We think this is the story that explains the bias. So I want to give you to distinguish 2 ways that I could give from input to output. So let's say I've got a monkey who's truly random typing on a word processor, and I ask myself, how likely is the monkey to type out the digits of pi on an n-key typewriter? Well, the probability of getting the first n digits is 1 over n. Sorry, the first x digits, is 1 over n to the power x plus 1. So I got to get the dots as well. And that's a very low probability, but it's finite and can be calculated. And in fact, that probability is the same for any set of sequences. It's the same for a sequence of all ones, for a sequence that has meaning to it, or for just a complete gibberish. So if a monkey's typing on a word processor, or an infinite number of monkeys are typing on word processors, input and outputs of a fixed length are all, outputs of a fixed length are all equally likely to occur. Now, what happens instead if a monkey were to type into a computer program like C? I pick C because there's competitions for writing shortest possible C programs, and one of them is to write a program that generates pi. The shortest one I could find on the internet is this 133 character code, which will generate the first 15,000 digits of pi using effectively a spigot algorithm. So now, if the monkey is just randomly typing on the typewriter, on the computer, sorry, then there's as long as they get the first 133 characters correct of the C code, they will generate the first 15,000 digits of pi, which would be incredibly unlikely to happen on a word processor, but there's some much larger probability that this would happen on typing into a computer. Interestingly, the University of Portsmouth decided to try this experiment with monkeys on typewriters. It's a big, very common cultural trope. And they found that the monkeys kind of had a predilection for one key, kept backing on it, and subsequently defecated on it. And that was the end of the experiment. They then promoted it to performance art, but that was more or less the end of the story. So monkeys are not truly random, but let's assume that they are. Then the intuition here is if you type into something that interprets your input to generate an output, you're going to find certain things that have short programs with much higher probability. And that intuition has been formalized very nicely in a field of mathematics called algorithmic information theory. It's based on the idea of Kolmogorov complexity, or Kolmogorov-Chaitin complexity, which says if you have a universal Turing machine, then the Kolmogorov complexity of a string is roughly speaking, the length of the shortest program on a universal Turing machine that can describe that sequence. So what it's capturing is something like this. If I have a sequence of just 0 1s in a row, the shortest program will be something like print 0 1 50 times, and I'll get the sequence. But a sequence below, which is 0s and 1s, probably does not have a shorter program than just simply print the sequence. And so we'd say that this one is effectively complex. Now, there's some warnings here. First of all, you can prove that Kolmogorov complexity is uncomputable due to the halting problem, but that doesn't stop us from getting some interesting intuitions from this, including that a random number is a number for whom there is no shorter code than just typing the number itself. So its Kolmogorov complexity is largely equal to its own length asymptotically. And also interesting things like the complexity of a set, the Kolmogorov complexity of a set, can be much less than the elements of the set. So the set for all numbers from 1 to Googleplex has some complex numbers in it, but the Kolmogorov complexity of the set, which I just gave to you, is pretty simple. And we're going to use that in just a minute. So this is a very important and beautiful piece of mathematics. And in fact, the concept of Kolmogorov complexity came slightly earlier by an American called Ray Solomanoff, who was thinking about randomly typing things into universal Turing machines. So it's a little bit like the monkey experiment, and typing in and asking how likely would you get a certain output. And so the argument goes a bit like this. If I have a universal Turing machine, so a computer that can do any calculation, I put random inputs, and say I'll simplify to binary now to make my life simple. And I type in these binary numbers, and I ask myself, how likely am I to get a certain output? Say, for example, the number pi, or the first x digits of pi. Well, I'll sum over all codes that generate that particular output, like the first 15,000 digits of pi. And so how likely am I to do that? Well, if I have a binary input, the probability that I type a certain code is 1/2 to the power the length of the code. So the probability that I get it is simply the probability of getting a code of length L, which is 1/2 to the power L, summed over all codes. And what he pointed out is that the most likely code is going to be the shortest code, which is effectively the Kolmogorov complexity. There's some technical things that you have to be very careful about. So it has to be a prefix machine, etc. But it's a very beautiful idea. It's the idea of algorithmic probability. And interestingly, Marvin Minsky, in one of his last public talks, said, it seems to me that the most important discovery since Gödel was the discovery of Chaitin, Solomanoff, and Kolmogorov of the concept called algorithmic probability. Everyone should learn all about that and spend the rest of their lives working on it. So that's Minsky for you on this. I'll quote him here. You can find it here on the YouTube link. So that's kind of fascinating, but this just basically gives you a kind of lower bound of the probability, because there are many other codes that will give you this. And so the question is, does this lower bound give you anything useful on the actual probability of getting an output upon random inputs? So how like the monkey problem, where the monkey's typing into your computer. And then there's a very beautiful theorem, Leonard Levin, called the coding theorem, which basically shows that asymptotically, this indeed is true. So this is the lower bound that Solomon came, but there's also an upper bound, which asymptotically is very close to the lower bound. So it's a relatively tight bound in the limit of very large strings. And the intuition that it's formalizing here is that simpler outputs, so outputs with small Kolmogorov complexity, are much more likely to appear than outputs with complicated, with large Kolmogorov complexity. Now, you might wonder why you were not taught this early in your academic career, because it seems like a very powerful theorem, but there are some pretty big problems with applying it. Among others is that it relies heavily on universal Turing machines. The Kolmogorov complexity is formally incomputable, although Minsky says in his little quote, the bit I didn't left out of his quote, which is that although it's uncomputable, approximations to it might be very helpful. And of course, it only holds in the asymptotic limit of large X. Now, here's where a physicist would look at this and say, well, this is a very strong prediction. It's basically telling me the probability upon random inputs is going to vary exponentially with a Kolmogorov complexity, which could vary perhaps quite a bit for different kinds of outputs. So I would be surprised if I relax a few of these things, that this effect would entirely go away. The typical physicist kind of intuition. And so with some of my students, we worked on this for a while, and we've come up with a much simpler kind of theory that works for any kind of input-output map, where you have some kind of map that maps inputs to outputs. And what you can do is you can calculate the entire set of all possible inputs. You can do this for a non-universal map, so a computable map. And that's a low complexity thing, because whole sets can be very simple to calculate. Then you can encode how frequently you find certain outputs with a very efficient code called a Shannon-Fano-Alias code, and that gives you a kind of probability that you get a certain code word. And this gives a bound for your complexity, because this is one way of generating your outputs. And so Kolmogorov complexity will be shorter than that bound. And this gives you, therefore, this bound here, which unfortunately is written in a Kolmogorov complexity which depends on f and n, the map and n. But luckily, if f itself is simple, so in other words, if f does not grow rapidly in system size, then we can show that this Kolmogorov complexity, this conditional complexity, is the first order given by the true complexity. That's still not enough, because Kolmogorov complexity is uncomputable. But what we can do next is that we say, well, let's just try approximating in one way or the other. So example would be, you can take compressors like various kinds of Lempel-Ziv measures, and these are some approximation to Kolmogorov complexity. And there's certain ones that have properties, asymptotic properties that are like Kolmogorov complexity, so it's good to try one of those, and then we just try, does this work? So we have now a simplified bound, which is that the probability upon random inputs that you get a certain output is going to be given by half to this Kolmogorov complexity. This is the same scaling that Solomon found, but we have a little factor a and b, which are two parameters that we put in that are fixed once for the map, so they're independent of x. And there's some ways you can calculate them in advance. So really, there's not a lot of fitting that goes on. You have an a and a b. What these are picking up to a large extent is a multiplicative and additive constants in your complexity measures. And so this is the upper bound. There's also a statistical lower bound, not an absolute one, but a statistical one, which we recently derived. And so the question is, does this thing work? Now we go back to the RNA system that I just showed you. So here's length 55 RNA. And now what I have on the y-axis is the log of the probability of getting it upon random sampling of sequences. So I pick a sequence at random, I fold it, I say what structure is it, then I write down the dot bracket notation that I showed you before, and I calculate the complexity here on this first here of the sequence. In this case, it's just a Lempel-Zip 76 compressor renormalized to get some Kolmogorov-like properties. And what you see is that this is a very simple structure. It's also the most likely structure, and these more complicated structures are much less likely to appear in this system. And here's our upper bounds. The dashed line is with A and B, and the black line is a kind of null model where B is set to 0, so there's only one parameter in there, which is A. So this is nice. We're able to say something very general about these RNA structures, which is that the structures that you find frequently when you randomly sample the sequences are structures that are very compressible, structures that have, in one way, they're low Kolmogorov complexity. And the reason for that is kind of simple. If I have a structure that is simple to describe, then many different sequences are likely to be able to describe it, and so it's going to have a lot of sequence entropy. Whereas if the structure is complex, there may only be one way of making it, and so the sequence entropy will be low. There won't be many sequences that map to it. When I say sequence entropy, I should be careful. I don't mean the entropy of the individual sequence, but the entropy of the set. So there's just basically the thermodynamic entropy. So just the log of the number of states. This trend holds for a wide range of other systems that we show here for the RNA map. Here's a set of ordinary differential equations that describe some circadian rhythms in cells. Here is an Uhlenbeck type financial model. Here's L systems, which are used in computer graphics, for example, to make plant-like shapes. Here is actually a input-output map that where we consciously break the one of our assumptions, which is that the map is simple. So this is a map from a input sequence to input vector to output vector, where the complexity of the matrix goes as n squared. So the bigger you make the matrix, you need a lot more information to describe it. That violates one of our conditions, and indeed, simplicity bias goes away. You can make algorithmic matrices, so matrices that have n squared terms, but for whom the description is very simple, and then simplicity bias comes back. I just point this out because what we found is that simplicity bias empirically works for a wide range of systems, even systems for which we can't formally prove that it should or shouldn't. And that's basically the idea there. So the upshot is we see the simplicity bias in these evolutionary systems, and these evolutionary systems have some fascinating parallels to learning systems. So you have some kind of fitness function you're trying to optimize in the evolutionary system. You have this redundancy with many more inputs, many more sequences than structures, for example. And that's the same kind of redundancy you get in overparameterized systems. And so the thought is, if you're having the same kind of structure you see in overparameterized learning systems, where you might be optimizing a loss function. So the loss function is like the fitness function, and the redundancy in the parameters that you have is a bit like the redundancy that you see in the sequences. So the idea is, I take this neural network. This is my child program. The education process is some kind of supervised learning. And if I have a neural network like this one, it's very simple: input, some hidden layers, and output. And I've got a bunch of parameters. Those parameters are the weights and the biases of this particular system. And yeah, so I should just, that's basically the system that I have. And what kind of surprised me initially was that these neural networks tend to work really well in this overparameterized regime. And just to remind you again of the thing I said earlier, there's this well-known intuition we have in physics, which is that you shouldn't have too many parameters. And it's beautifully expressed by the late Freeman Dyson in this paper, where he talks about going to Chicago to talk to Enrico Fermi about a theory he had, elementary particle theory. And at some point, Fermi asks him how many parameters he had, and Dyson says 5. And then Fermi says, well, with 4 parameters, I can fit an elephant. With 5, I can make it wiggle its trunk. And recently, a group, the American Journal of Physics, showed that you can indeed model an elephant with 4 parameters, and with 5 parameters, you could wiggle its trunk. Fermi claims that this came from John von Neumann. So von Neumann's intuition was impeccable in this case. The point, of course, being is that if you have a lot of parameters, then it doesn't become predictive. And this intuition, you can see in many situations that we're used to. So let's say, this is what we do for undergraduates. We give them a bunch of data points and say these red dots. We say, now fit some kind of polynomial function to it. So here's a polynomial function, and we fit it. And if I have got 10 data points and I fit a 5th order polynomial, I'll do okay. I won't fit all the data perfectly, but I won't go crazy. But I put a 20th order polynomial and I fit it, unless I do some kind of regularization, I'm going to get essentially nonsense. The reason being that the 20th order polynomial has a very large number of possible functions that can fit this data, and if I just randomly look for ones that fit it, I'm going to find very likely something that that fits the data, that gives me something that intuitively looks wrong at bits where I have no data to constrain it. Now here I just show you this here for the simple regression problem. If I take a very simple neural network with different numbers of hidden layers, in this case several thousand parameters, it turns out that the neural network fits this thing with a relatively smooth function, and doesn't seem to show this overfitting behavior that you get for the simple system. And that's surprising. It was surprising to me at first, because why would the neural network do that? In principle, neural networks are incredibly expressive, so a neural network can reproduce this very complicated function. And the question is, why does it prefer this simple function? What's the inductive bias that it has to give a simple function as opposed to this very complex function? It's a kind of very fundamental question. And the conundrum is basically this: if DNNs are highly expressive, why do they pick functions that generalize so well? And here's a famous paper by Zhang et al. From the group at Google, who basically showed that if you take an image data set, in this case CFAR10, so there's these 10 images, you train a neural network to recognize images, it does pretty well. What they then did is they randomized labels, so pictures of airplane had automobile on it, etc. And so there's not a lot of structure in the data anymore. And what they found was with SGD, stochastic gradient descent, they could nevertheless train to 0 training error, so the system could perfectly fit the data. And of course, if you then gave it new correctly labeled data, it would not predict at all, because it effectively memorized the data. And what that's basically telling you is it's demonstrating something that we knew already theoretically, which is that these neural networks are extremely expressive. So just 1 second. Ladies, I'm giving a talk. Okay? Go tell mommy that is going to be late. Okay? Sorry, my kids are coming in. So the point here is that what this story tells us is that neural networks are extremely expressive, and that you can actually train them pretty accurately to get to 0 training on really crazy data. So let's get back to this Boolean question. Can we try to learn? What does it tell us about learning on a Boolean system like the one I just showed you of the COVID-19 doctor? And so I'm going to try to bring these two things together. So if I'm learning a neural network, the intuition that I've now gathered from the AIT is that there is a map, in this case, not the map from the inputs of my machine learning system, which would be the examples of what the doctor would do as a function of the answers of his patients, but rather what the parameters are. And if I randomly pick the parameters, what function do I get? So if I take a neural network and I randomly various parameters, what function will it give for this particular Boolean system? The system is nice, it's simple. It's the kind of thing physicists like to work with. We understand more or less what's going on. And so, well, there's a few things we can prove. So this is something we proved. Chris Mingard, as an undergraduate student, actually proved just for a very simple system like a perceptron with weight set to 0. If you randomly pick inputs and ask yourself how likely you are to get a particular output function, then the probability that you get a particular output function of a certain entropy, which is the number of zeros and ones in your function, is equal for all different entropies. So you're equally likely to get a function of all zeros in a neural network as you are to get a function as you are to get all functions with half ones and half zeros. That's basically what it's telling you. So that tells you that you're much more likely to get functions with low entropy, simple entropy, like all zeros, because there's only one function of that type. And there are many functions with, very, very many functions with half of ones and half zeros. This is basically what this thing tells you. And then here you see something which looks very similar to the other input-output maps. So here Guillermo basically took a 7-bit string, so it's not 9 but 7, but essentially the same as the Boolean question we had. We imposed a particular Boolean function which says on all 2 to the 7, which is 128 functions, we tell you whether it's true or false. We then give the system half of them as a training set. We train a neural network and then ask how well does it do, what function does it then produce. Sorry, take a step back. In this case, no, we didn't do that. In this case, we simply randomly chose the parameters and ask ourselves what Boolean function does it produce. And what you see is that this thing is highly biased. So a certain small subset of functions are very likely to appear, others are very unlikely to appear. Since there's 2 to 128 or 10 to 38 functions, a naive null model would be that every function appears with a probability of 10 to the minus 38. But in fact, what you see is that there are functions that appear with probability as high as 1 in 10, and this is the trivial function. So if you take a Lempel-Ziff complexity measure as kind of a proxy for complexity of the functions, then what you see is these things are exponentially more likely to find simple functions than complex functions. And this particular bias has an impact then on generalization. So, for example, if now I am doing a supervised learning experiment where in this case 64 of my data points are given to the system so it learns, and then it's got to guess what the other 64 answers would be. And what you see is that the more complex you make the target function, so the higher its complexity, the worse that the system does. This is a system which is trained by SGD to find a 0 error training set, and then you test it. And what you find, which is kind of interesting, is here I've got a scatter plot where on the y-axis I have generalization, and the x-axis I've got the Lempel-Ziff complexity. This is for a function whose the target function has a 38.5 complexity, so it's about here. I give the system half of the answers, and you see that it tends to find solutions with complexity not too far from the target function. Here I have a random learner that basically just, all it does is it just fixes the first 64 bits and randomly picks one on the other 64. They're still consistent with the training set, but of course they generalize terribly badly. And what you also see is that this inductive bias for simplicity only helps you if your targets are simple. So in other words, if you're trying to learn something which is effectively simple, then this bias for simplicity will give you good generalization. If you're trying to learn something complicated, it won't help you at all. In fact, it might even harm you, make your learning go less well, which is loosely a kind of a no free lunch type of argument. So this is interesting because this tells us that these neural networks should generalize really well if they are in fact learning simple functions. They should generalize poorly if they are trying to learn complex functions. So we can ask ourselves, well, are the functions that we see in nature simple or not? Well, actually, if you think about that Boolean example I gave you of the COVID-19 doctor, then it's very likely that there are all kinds of correlations between answers that this doctor would give. And so you could probably learn the actual function that she uses is not going to be that complex. So our intuition is that a lot of things that we find in nature are effectively described by simpler functions. And you can see that with other data sets. So take something like MNIST, for example, which has 784 different input. That's the 28 by 28 pixels that it has. But you can work out what the effective dimension is of the underlying structure, and it tends to be on the order of 15 on average, and it can be down as low as 9 or 10 for some of the simpler adapters. So this tells you that when you're learning an image like MNIST, you're learning something much simpler than the kind of random null model would be. Now, the problem that I'm sure a few of you already picked up is that in this case, I am training not by randomly sampling parameters, but I'm rather training using stochastic gradient descent, which is running down the gradients of a loss function. So why on earth should a simplicity bias upon random sampling of parameters have anything to do with the way that stochastic gradient descent finds minima? Well, there's a kind of simple intuition that we also use in the evolutionary system, which works a little bit like this. I say this is your loss function, and this is some kind of parameter that you're looking at, and this is function 1, this is function 2, this is function 3. Let's say all these functions give you 0 error on your training set, but this one has a much larger neutral set, or in other words, a much larger set of parameters that give it, which would be a much larger a priori probability, whereas these ones have much smaller a priori probabilities upon random sampling. Then what SGD does, it starts somewhere at a high loss function and it follows gradients down, and it stands to reason that the size of the Bayesian of attraction, so the size of the total number of parameters that you start SGD with that would converge on F1, is going to be correlated with the size of the Bayesian. And if that's true, then you would expect that functions that when you train with SGD, that the probability that you find a particular function to fit your data correlates with the size of the Bayesian. And here's a kind of slightly more formal Bayesian way of thinking about this. So let's say I pick a fixed training set. I have some prior over functions, which can be the prior, like the one that we just showed you on the previous page. And then I need to have some likelihood. Well, in this case, if I train to 0 error, the likelihood is basically 1 if my function that I find is correct on all the input data points, and it's 0 otherwise. And then the posterior simply follows from Bayes' rules. The posterior is the probability that I get a certain function given that it's consistent, or it's conditioned on S, it's consistent with the training set. And that's just given by Bayes' rule, whereas the prior, this is the likelihood, and down here is the marginal likelihood or the evidence, which is simply the sum right here. It's the weighted sum of all the probabilities of all the functions that fit the training set. And that's kind of interesting because once I fix my training set, this marginal likelihood is constant, okay? This also gives me 0 or 1 for all functions that fit the training set. So therefore my posterior is going to have the same bias as my prior. It's just going to be normalized in a slightly different way. But for every function that fits my training data, the likelihood of that function is going to be proportional to its prior. And so what we then did is said, well, let's look at these functions and ask ourselves how likely are they to appear on 2 different scenarios. So here on the y-axis, we basically calculated, in this case, using a Gaussian process approximation, which is something technical, but we think works pretty well. The probability that you get a certain function for an MNIST system, and here we've got the SGD, probability the SGD finds that function for a certain MNIST system. What we have done here is we've used MSE loss, we've used the training set of 1,000 MNIST images and a test set of just 100. We use test set of just 100 because that is small enough to give us some finite probabilities. And what you see is that on that particular test set, the most likely function that's found with the probability quite similar for both the random sampling and for the SGD is a function with 1 error. here's a function with 2 errors. This function right here is a 0 error function, so it is found occasionally, but fairly rarely. And what's fascinating is that the probability that these functions appear upon random sampling, which is proportional to the prior, is very closely linked to the probability that they are found by SGD. To give you a sense of the scale of this agreement, I have in this plot here a different experiment. So this experiment, we simply randomly, we find different random functions. So we take a function, train it to 0 error. It gives you conditioned to have 0 error on the training set and some finite number of errors on the test set. And then you ask how likely are those functions. And so here you see, for example, function with 100% errors are extremely unlikely, probability 10 to the minus 200 that you get the normal random sampling. And in between, there's a wide range of functions. And this little red box right here is the stuff that SGD actually finds, which are, of course, the very high likelihood functions. And those happen to be the functions with extremely low error. So why does SGD generalize well in this MNIST system? Well, it's because it finds with high probability function with low generalization error. That's a bit of a tautology, except that here we show you exactly how they find those functions. There's a range of probabilities that you can get from doing this Bayesian argument based on the prior, and the likelihood that you find them is extremely well predicted by this simple system. We've also looked at the complexity of these functions and show, not so surprisingly, that the functions that have low error are simple. So here's their complexity. This is a different complexity measure. High probability, low error functions have lower complexity, and complex functions have higher complexity. This case was done for plain vanilla SGD. Here we do it for somewhat less sampling, but for AdaGrad, which is one of the other ones. Here we do it for this is called NTK, but I'll skip that for now. We do this as well for CNN, so convolution networks, for an LSTM on a database from the IMD movie database, with a sentiment analysis database. And what you see in each of these cases is that you get reasonably good agreements between the probability that SGD finds a function with the probability that you get it upon random sampling of parameters. There's a lot of technical steps here that I'll skip over, but the upshot is basically that SGD and this Bayesian approach give you quite similar results. And this surprised us that they worked out that well. I mean, it'd be great already if you found that the functions found by SGD were in the same box as the functions found by random sampling. But we're finding something much stronger. The actual, within that box, within that very tiny, minuscule fraction of all possible functions that can fit the data, a very tiny fraction dominate what SGD finds, and those are the ones that random sampling would also tell you are the most likely ones to be found. And that's kind of cool. Just remember that there are, even for the set of 100 of just 100 test set of size 100, there are still, this is a binarized MNIST, by the way, I forgot to say, there are still 2 to the 100, so 10 to the 30 possible different functions that fit the test set. And so SGD is hugely biased towards a small subset of them. And what we're arguing here is that the primary thing you're seeing is that SGD is following the kind of Bayesian prediction. You can do other things. You can play with different kinds of algorithms, so RMS prop, Adam, but they all show somewhat similar behavior. Here, just to check, we did different test set sizes. Here's a small test set, so errors are sort of part of a small training set, so the errors are clearly smaller. Here's a slightly larger training set, an even larger training set, an even larger training set. So as you make the training set larger, the number of functions that you find goes down because functions are being killed off by the training set, as it were, and your error goes down. So those are the kinds of things that you see. So the upshot here really is that the probabilities that functions are found by SGD is remarkably close to a Bayesian sampler. We do this for MNIST with fully connected networks, and for fashion MNIST, which is a more complicated data set with convolutional networks, and for this IMD data set with LSTM. Exactly why this works so well is not so well understood, but heuristically, this must stem from the very large bias. In fact, for unbiased systems, so if we randomize the data, the system becomes a lot less biased, and the correlations become much less strong. And this is nice because we can then use a Bayesian picture to understand generalization. And so I'm going to try to do that for a minute. So there's really, I should have said this earlier, but when I'm thinking about generalization, I'm really asking two questions very often. One is, why do these neural networks generalize at all in the overparameterized regime? Like, given that neural network can fit any function, including, in that case of size 100 test sets, any of the 10 to the 30 possible functions, most of which are really bad, why is it biased towards a simple subsets? And we've changed that question. I think for that question, we'd say, well, it's because it largely follows the implicit, it's an implicit bias that you have already in the prior, and that's why, since SGD, when you train it, follows that, that's why it does well. It doesn't quite answer yet why there is that bias, and for the reason why there's that bias, it may be that simplicity bias is one of the reasons. So another question, which is the most common one studied in the literature, and it's important to distinguish it, which is that given that a neural network generalizes, can we further fine-tune the hyperparameters to improve its generalization? And that's basically asking questions like, if I change the batch size, etc., does it work better? But I'm looking really at question number one. And so question number one is linked heavily to what we might call generalization bounds. My student Guillermo pointed this theorem out to me, or he derived this corollary of a very well theory from David McAllister called pack Bayes, which basically says that the error that you get on a test set can be bounded by the log of the marginal likelihoods plus some small other terms, basically have to do with the size of your training. This is the size of the training set and the error that you're willing to accommodate. And so what we did is we tried that bound. So this bound basically tells you what it's a bound on the error. So the error is going to be larger than this. And here you see for a number of different systems. So here's a convolution neural network with 4 layers. And here we corrupt the data a bit like what Zhang et al. Did. So as you corrupt the data, you generalize less and less well. We binarize it again. So the worst you can do is 50% correct. And what you see is that for a simpler thing, you do like this. That's the blue line, that's MNIST. Then there's something called fashion MNIST, which is slightly more complex. And then there's CFAR, which is even more complex, which is this green line here. For each of these, the solid line is this pack Bayes bound that we derived. And it seems to describe quite nicely what the generalization, how the generalization changes as you change label corruption. And this is interesting because it's in some sense telling us that this theory, which is based on the marginal likelihood, can correlate very nicely with the kind of error that you find. Another thing which Guillermo has done recently is you can look at learning curves. So how does the generalization error change as you increase the number of data points? So here you see this on a log-log plot, something which has been shown by others, which is that different data sets have almost different scaling laws. And so this is MNIST, the light blue line. And this blue one is the pack Bayes as a function of the size of your training set. And here is fashion MNIST, which is slightly more complicated. Here is CFAR. In each case, what you see is that the pack Bayes is reproducing the same, or roughly the same kind of exponential scaling behavior. And that's encouraging because that tells us that this theory, which is basically based on this Bayesian quantity, it's not a fully Bayesian theory, but this Bayesian quantity, the marginal likelihoods, is able to capture a lot of the behavior that you see in trained DNNs, because these dashed lines are, of course, for SGD trained DNNs. And we can do a bit further. So in the previous Bayesian thing I showed you, I did that for a single fixed, training set. But now we're going to try looking at something which is not a fixed training set. I'm almost at the end of my talk. I see I had a stray slide there. And this is something that Greg Yang pointed out to us, Greg Yang from Microsoft, and it was a very nice paper he just recently wrote with Hadi Salman. And he pointed out that for some nonlinearities, like tangent nonlinearities, from which we know that there is an ordered phase and a chaotic phase, that this bias that we had shown previously for the Boolean system starts to decay. So here you see for a tangent function, as you increase the width, the Gaussian width of the parameters that you choose on your initialization, you start seeing for wider networks, that the bias starts to become less. Or if you fix the width and you increase the number of layers, the bias goes away. It's not something you see for ReLU at hardly at all. It's something that's particular to these TENG or Earth-like nonlinearities. Now, you wouldn't use a neural network in that regime, but what's super interesting is you can then do a test of our theory. So we say, look, for this to generalize well, the system needs to be highly biased. Now we have Greg has shown us a way of tuning the bias and basically making it less. And so what you see is here I've got 2 layers, 5 layers, 10 layers with 1, 2, 4, and 8. So as I go this way or that way, I get more and more into chaotic regime. You see that my probability complexity curves become less and less biased, as you see here. And so here you see almost nothing because I haven't sampled enough. And lo and behold, here I've got the generalization error versus the Lempel-Ziff complexity. And for this one, which are equivalent to each other, I get, I get pretty good generalization for simple functions, not very good for complex ones. But by the time I get down here, where I've got not that much bias left, I'm not doing very well in simple functions anymore. And that's simply because my neural network is no longer biased towards the simple functions. And so it's picking one of the very many other functions that it could possibly pick. And so you can do some other interesting things with this. You can then say, well, can I understand a bit better what's happening in these systems? And I can. And I'm coming out to the end of my talk. So what you can then do is you have a target function, you've got a test function, there's some error that you have. And if you average over, if you average your posterior over training sets, and you try it for a lot of different training sets, then this is just Bayes' theorem, then we know that this likelihood is just 1 minus the average, the error of that function to the power m, because I try m different times, right? M is the size of my training set. And so now I have something quite nice, which is I've got an approximate theory that tells me what how my posterior likelihood depends on my prior and on the error, the structure of the errors that it has. And this is just capturing the intuition, which is, or this is formulating the intuition, which is that if you have a large function with a large error on data, then it's unlikely to survive a training process. And so what we did for this Boolean system is we tried for a particular target function, this is the target function, a wide range of functions at different complexities, and then calculate 1 minus epsilon f. And this is taken to some high power. So if you have a large error, then that tells you that function is unlikely to survive training. And you see this here for this particular function. So as you increase the m, which is the size of your training set, from 1 to 100, there's 128 possibilities in total, you see that this your posterior gets more and more affected by the training, and a smaller range of functions will survive the training set on average, the training process on average. And what's nice is you can then do experiments SGD, and I'll just show you kind of classic experiment like I showed you before. So here's a generalization error. Here is the Lempel-Ziff complexity. This is for a simple network without chaos in it, so one that's highly biased. This is for an unbiased network. You see that for this particular function, I'm finding these functions typically with more moderate generalization error, whereas for this unbiased network, I'm finding functions that are up here. And what's nice is if I look at, then here I've got plotted on the top and the bottom, basically distribution of the complexity of the functions that I find. This is a histogram of how many functions I find for each complexity. And you see that you find this histogram for the more biased network, and this higher complexity histogram for the unbiased network, because it's getting the entropy of the very large number of possible functions is starting to dominate over the bias. And so here we have our little Bayesian experiment or calculation. And here's what we measure in the SGD, and they're relatively similar, which is very encouraging. And so what you can then do is you can then do this for a series of different systems, and you see that if you've got a simple target function and you've got a simple neural network, then you tend to find lots of functions that are simple and not very functional complex. And as the system gets more and more complicated that you're trying to learn, you find that your highly biased network isn't as good and gets closer to the more complex one. And the same thing you can see now for MNIST. For MNIST, I don't know what the complexity distribution is or the error distribution is, but I can do something else, which is, in this case, I have 3 different learning systems. The blue one is for 2 layers, the orange is for 5, and the green is for 10. And here I have this thing which makes me more and more and more chaotic, and therefore less and less biased. And what you see is that if you have a small training set, as you see here, then as you get into the more unbiased regime, so you're having a lot of functions that are, you have a very much larger number of complex functions and simple functions that would be close to the true MNIST function, you start getting this enormous drop in generalization down to, say, 20%. This is on full multi-class MNIST. As you increase the size, so here's 1,000, there's 5,000, there's 10,000, now 50,000. Now you see it goes from 98% to 92%. So now the very strong effect of the training is that you've kicked out a lot of those complex functions, of which there are very many, but we typically have a slightly larger error. So what this shows you is that there's this interesting interplay when you are doing machine learning, and that interplay is between an intrinsic bias that you think these systems have that are needed to bias you away from the very large number of complex functions that fit your data but that generalize poorly. And that as you change the size of the training set, you can mitigate that effect. So just to conclude, we're saying that deep learning may work because deep learning systems have kind of natural bias towards simple functions, Occam's razor type of argument. We show evidence that SGD behaves like a Bayesian optimizer, which is a little surprising, but it seems like that works pretty well. And given that it behaves like a Bayesian optimizer, we can use things like pack-Bayes to provide tight bounds. And I've just sketched for you really a kind of Bayesian approach that lets you see how both the error distribution of functions and training and the prior, so the bias, together can help you explain how generalization works. And as always, this work was done by students. So Guillermo Valle-Perez, who's able to answer some questions in the Q&A, and some very bright undergrads, Chris Mingard, Joris Galse, Henry Rees, and more. And with that, I thank you for your attention. I apologize a little bit for running over, and see if I can take any questions.
All right, thank you very much, Art, for this great talk. There's an open question, and people can feel free to enter more questions as you answer it. Can you see the question, Art?
Yeah, yes, I'm trying to think about what the so I'll say it's very nice work. So that work on mapping, trying to map some aspects of learning to regionalization group. I have not had time to think about how this connects to what we're doing. I'm pretty sure it's different, and the reason is that what we're arguing is effectively a kind of non-parametric. It's a non-parametric argument. It's non-parametric because it doesn't really depend that much on the exact way the parameters work. So this is an argument that is true for the following reason. The probability, so that there's the null model that we're putting forward from simplicity bias basically says the probability that you get a particular function is proportional to the complexity of the function. And as long as your neural network is expressive enough to express all the functions that matter, then this gives you a kind of 0th order prior that you would expect. So how likely you expect a certain function to appear, and it's independent of the exact neural network that you use. Now, in practice, we all know that there's significant improvement you can get when you change your architecture. And in fact, when we actually measure the priors, we see, for example, we showed that if you take a CNN and you include max pooling, then the prior for the 0 error function goes way up. on image data, in this case fashionedness, which is not unexpected because the max pooling is trying to increase the inductive bias towards image-like functions. So what I'm trying to say is that basically the kinds of the null model making is just saying that the probability of a function is proportional to the exponential of its complexity, or one over the exponential of its complexity, and that's just a property of these kinds of systems, and that these higher order effects that you get by changing the architecture, for example, which are super important in practice, are really where the details of the parameters come in, and that's what, if I understood it right, is still part of what the RGA argument is trying to make. Good.
Okay, there was another question asked in chat. Can you please, do you have any opinion on the relation of your work with the lottery ticket hypothesis?
Remind me what the lottery ticket hypothesis is. I remember having heard it, but I forgot what it was. Perhaps the person who did this could remind me. I remember thinking about this and I've forgotten what it was. The answer is no. The answer is no. I think. No, go ahead. Somebody's asking.
No, the lottery ticket hypothesis is just an hypothesis that mentions that since we're training with such huge models, there's a subnetwork within our huge neural networks that has a very good initialization for finding a good solution.
Okay.
So,
okay, so that's a different, that I was misremembering, and that's not something that I'm familiar with. And if you could send me a paper to on that, that sounds really interesting. I mean, there is a fundamental link here to a kind of compression argument, right? So you say, well, those functions that have a large volume of parameters that map to them, which we say are the simple functions, are the functions you can easily find. But that also tells you that there's a huge redundancy in the system, and so there also exists a much simpler system that can also generate that function, which is a corollary of it. So you can, in other words, compress your networks a lot more for functions that are simple than you can for functions that are complex.
Can I add something to that? So like as far as I remember, the lottery ticket hypothesis says something like very specific, which I don't think is like very directly related to us, because it's, you know, it's this observation that there is like a subnetwork such that if you only use those weights at the initialization that it was originally found, you can train it successfully. There's like a very specific thing. But if you think about a more general thing of like, oh, there's subnetworks in the neural network at initialization which are good for the task already, then I think there is some relation to the work that we have built upon on like infinite width networks, because people have some intuition that infinitely wide networks, I mean, because there's infinitely wide, there is just by probability subnetworks there which are solving the problem, and therefore just by tuning the top layer to focus on those subnetworks, you can learn the problem. And so there's that connection with this work on infinite width networks, which we build upon. But I mean, it's not the focus of what we do. But
That's an interesting question. Good. Sorry, that was. I'll have to think about that more. I'll see if there's any other questions. Let's look at the questions that were done. One person asked whether the simplicity bias are bounded by lines with the same slope, but there are others with different slopes. Is universality in the slope? And the answer to that is there's not universality in the slope because that depends on the prefactor A, but the prefactor A we found in practice tends to vary very little. So there's some kind of near universality in the slope. But you have to be careful with how you measure the complexity. So if you use a different measure of complexity, then it's very possible that two measure complexity correlate with one another, but with some other prefactor as well. But it would be very interesting to think about whether there is some kind of universality that some kind of fixed point that we're not quite at. Don't know.
Maybe it's good if you read out the question and then answer it.
Yes, thank you. Okay, so I'll do, and yes, that was this question, and then another question was.
There's one on double descent, which I just like I was typing the answer, but I sent enter before I finished the type.
Okay, so yeah. So there's a question here. How does this presentation? Okay, how does this presentation fit with the double descent phenomenon we are observing recently in deep neural literature? Is he fixing number of data points and learning algorithm, increasing complexity, reduce generalization error, and then improve generalization error? Yeah. So what the double descent phenomenon is basically telling you is the following. What people are observing empirically, and let's say some people like Montanari and others have done analytically in certain somewhat odd limits, is that what you see with generalization error is initially the kind of bias variance trade-off that you're used to, which is for a very small number of parameters, you have a high bias because you don't fit very well. Then you go through a minimum in your generalization error, and then it goes up again as the number of parameters reaches the same, is similar to the number of data points. In fact, in those theories, it diverges, and then afterwards it goes down again as you increase the number of parameters. So that's what they call double descent, because you first descend down as you increase the number of parameters because your bias goes down. Then you have the kind of classic bias variance trade-off thing, and then afterwards it goes back down further. But what we're seeing here, we are not sure that what we're seeing here is quite the same as what people see in these double descent curves, because they typically need some kind of noise in the system, and it's in a slightly funny limit, right? So you've got everything set to infinity. So we tested it on a few, when we first saw this, we tested it on a few neural networks by just changing the number of parameters. So on the Boolean system, and we didn't see any double descent phenomenon. But it's a super interesting thing to ask. And there's probably a correlated question to that, which is, what is it about systems that allow you to have good generalization in the overparameterized regime? We've given one hypothesis, which is that there is an idea from AIT of simplicity bias, which tells you that these neural networks are biased towards simple functions. But it doesn't tell you why these neural networks happen to do that very well, and whereas perhaps why another learning system which doesn't generalize well and shows classic bias variance trade-off behavior does not show a double descent, and therefore does not generalize well in the overparameterized regime. We just understand it. Good. I think I've done the questions, have I? They're very good questions. Make sure I've not missed any.
There are no open questions at the moment.
Super. Great.
There's one.
Okay. All right. Then there's that. So I'll take them. One of them says it's intuitive that between a high proportion of parameters versus samples, the accuracy will be declining. So have you experimented with regularization techniques, specifically with weight decay? It is related to the problem of finding the ideal number of parameters. So we have experimented with some regularization techniques. Actually, one of the future projects that we're going to look at is looking at the probability that you find certain functions So that's that. Those those plots. Like I'll show you one of them again here. The plots where we try to say that SGD behaves similar to a Bayesian system. And so you can ask yourself questions like, if I add a regularization technique to this, does that increase the probability that I find functions with low error or not? And if that's true, then that might help us understand a little bit better what these regularization techniques are doing to the bias, right? So what you want in any learning system is that you've got an inductive bias towards functions that generalize well. And what some of these regularization techniques claim to do is to generate that kind of a bias. We've looked at briefly weight decay, but we haven't seen anything very striking yet, but we haven't tested it very carefully either. Like, one of the problems in this field is that the actual amount of literature is so vast that one often feels like you're missing big chunks of it, which is impossible to keep up with. So if anybody has any links to things they think we should study, and they could point us to a particular paper to look at, that would be highly appreciated. And then there's one more question as well from Ricardo Ziquina. So do you see any connection with the high local entropy results? I'm unfortunately not familiar with the high local entropy results. Maybe I could say the following, which is that what we're arguing is a kind of entropic argument, right? So we're basically saying, in the set of all functions that can fit the test set, of which there are typically hyper-astronomically many, there is a very big difference in their entropy, which is the number of microstates, so the kind of thermodynamic entropy, the microstates that map to that function, and that entropy can vary over many orders of magnitude. And so if you're at zero, if you think of very naively of your system as a kind of entropy enthalpy, where the enthalpy is the value of your loss function, once you're down to very low loss, then the entropy is going to be the dominant factor that gives you one function over another function. So that's basically that.
I wonder if the local entropy refers to like flatness, maybe.
Yes.
You know, like the label.
Okay, flatness. Okay, super. Yeah, so that's okay. Thank you. Thank you, Guillermo. Thank you for answering that question. So actually, I didn't show the results here, but we have a project which we're hopefully writing up soon on connections to flatness. So flatness is basically some kind of, it's a local property. So I run my optimizer, I find a particular function, then I locate the parameters and ask myself, for example, if I take a Hessian, are the eigenvalues small, then I'm flat. That means that I can vary the parameters without changing the function that much. So it's a kind of robustness, like, and there's a whole series of them, of different measures that are all sensitivity-based measures that are all hopefully equivalent to each other. And what we find, and this it goes back to Schmidhuber and others who claim that so flatter solutions generalize better. And what we find in general is that there's a link between this local flatness and our kind of volume measurement, which is the probability that you get this function upon random sampling. And these two are strongly correlated. And so that's not surprising they're strongly correlated, but they are strongly correlated. In fact, it's known in the evolution literature, which has a lot of overlaps with this, that's the case. So larger neutral sets have much higher robustness, and therefore this is analogous in some sense to that. The problem with flatness measures is you have to be careful how you measure flatness, because flatness is a local quantity, and there are certain symmetries that neural networks have that allow you sometimes, if you're not careful, to take one of these local flatness measures and you can basically increase it arbitrarily, and when you do that, you'll still have exactly the same function, so the same generalization. So what we're going to say in this paper is that flatness is a good, quick and dirty way of seeing whether you found a good solution, because it correlates with the volume, which is a harder thing to calculate. but you need to be careful. So for a function with a large probability, a large a priori probability or a large posterior probability upon training, a large prior, will typically, on average, have higher flatness, but it will always have regions of its space where the flatness can be not very good, but the function will be the same. I think that's a simple way of saying
it. It is just a matter of that is just a matter of fixing, some overall volume, right? Like the total normalization of the weights, or just take binary weights for simplicity. Then you would get rid of all these invariant properties.
Pardon, say that again. Take what kind of weights?
I mean, if you just take binary weights, for instance, for the sake of simplicity, you get rid of all these rescalings and all these, let me say, trivial symmetries.
Yeah.
But there may still be regions in the neutral set which have much lower robustness than others, right?
Yeah. So we've actually So we've looked at this as well. So we've taken not binary, we've just discretized the weights. If you discretize the weights, then it's quite easy to measure this kind of local robustness, which is basically if I have a function and then I tweak the weights, how likely am I to keep the same function? Right. That's effectively what these local entropy things are measuring. And there is a correlation basically between the local robustness and the log of the probability. So log of the overall volume. And that's also seen in a wide range of systems. I mean, it's interesting to think about local measures that you can use because they're typically quick to calculate. And so
actually, in the case of what is called local entropy, is actually not really local, in the sense that one can show that in networks, non-convex networks, that are storing random patterns, you can find flat regions that have a size which is of order n. So it's really a fraction of the volume, and so it's not like measuring the eigenvalues of the Hessian. It's really almost an extensive property, and this happens also when there's nothing to generalize. Yeah. So when you just learn random patterns, which means that somehow, as you were mentioning, neural networks have this intrinsic bias towards this kind of robust solutions.
I'd love to see some work on so this is basically a property of a network property, yeah. It's just a generic network property, so that's super interesting. Is this Ricardo speaking? Yeah.
Yes.
Yeah. Okay. So I think I should look up your work because I've seen things that you've written. So it'd be interesting to see. But if you have any thoughts on how this connects, please send us an email. It'd be interesting to look at.
Thank you.
Yeah. Good. So thank you very much for those very helpful questions. I think I've answered all the ones that were put to me. I hope that I've given some flavor of our kind of slightly crazy ideas about why neural networks generalize so well. But if you have any other thoughts or things you think we could think about or learn from, I'm always very happy to hear from people in the audience. It's kind of strange because I can't see anybody, all I see is my screen. But it is a great pleasure to speak to you, and I thank you for your attention. And I think we've come to the end of our time. Is that right, Fabian?
Yeah, and I don't see any further questions. So thank you very much, Art. It was a great talk.
Thank you.
Thanks everybody for joining in.
Thank you. And I'll send you my slides, Fabian.
Yeah, thank you.
Super.
We'll make them available on the webpage.
Yeah, super. Thank you.